In this video, we're going to talk about implicitly defined functions. All right. So first off, explicitly defined functions. Those are most of the functions that we've been using throughout the course. Right. Those are functions specified in the format f of x equals, and then over here some formula involving the variable x. Or in this format, y equals f of x. Again, this is a formula over here just involving the function of x. So anytime you have functions specified like that, those are just explicitly defined functions. They tell you exactly what functions we're using, and you don't really have to worry about anything else. So we've also seen in the past couple of videos, right, that functions can also be defined by equations. But, right, not all equations will define y as a function of x, at least when you consider them as a whole. Okay. There is something called the implicit function theorem, and I'm not going to go into the details of that because it's a pretty complicated and technical theorem, and it's not really something that we want to go into in great detail, but we do need to sort of understand what the implicit function theorem says, and it says that even though an equation may not define y as a function of x globally, under the right conditions, you can find smaller parts of the equation, right? And by that I kind of mean the graph of the equation that do define y as a function of x. And so we've already seen that in the case of this function right here, x squared, or this equation, x squared plus y squared equals 1, right? And then if you recall in the previous videos when we solved for y, we got basically two pieces. We got y equals square root 1 minus x squared and y equals minus square root 1 minus x squared. So again, just taking a look at the graph, right? Here is the graph of x squared plus y squared equals 1, right? That's the unit circle, right? The circle centered at the origin of radius 1. And that does not define y as a function of x, right? Because it doesn't pass the vertical line test. There are tons of vertical lines that cut through that intersect the graph of the equation in more than one spot, right? But when we solved for y, we got two pieces. We got this piece right here, sort of the upper half, and that's defined by this function, y equals the square root of 1 minus x squared. And we got the minus version of that, which is the lower half of the circle. So even though this whole equation, right, didn't define y as a function of x, the implicit function theorem tells us that you can find smaller pieces, right, that do define functions of x. So not the whole equation itself, right, but smaller pieces that are actual functions in there. So that's what the implicit function theorem says. Okay, and in this particular case, we can actually figure out what those some of those functions are. So the smaller parts of the equations that do define y as a function of x are called implicitly defined functions. So this equation right here, even though it doesn't define y as a function of x, it does define these two smaller pieces here, the parts that are that we get from the implicit function theorem here. Okay, so anytime we have those kinds of functions, they are called implicitly defined functions. And now, when I first saw this concept, I thought, well, okay, great, I can see, that I do get some functions out of here, but why can't I just solve for y every single time and then not have to worry about implicitly defined functions? And well, the answer is, right, goes back to the fact that in practice it may be difficult or impossible to ever do what we did here. In other words, we may not find these functions that are guaranteed by the implicit function theorem. So we may never know what they are. In this case we did, right? We had this equation, right, and it defined some functions, and we were able to determine what those are, explicit formulas for those two functions. All right, so but the downside to this is that we may never be able to figure out what those explicit formulas are. It may just be too complicated to do that. Okay, so sometimes we'll be working with those functions and we'll never really know what they're their formulas are. And it turns out, though, that for what we want to do, that's okay, right? What we want to do is to take the derivative of these implicitly defined functions. And we can do that even though we don't have explicit formulas for them through a technique called implicit differentiation. And in the next example, we will go through and we will take the derivative of this implicitly, and we will take a look at that.